Hello and welcome to the channel. Our mission today is pretty specific, actually. We are looking at how you provide secure, identity-aware access to dynamic on-prem infrastructure. Think Kubernetes services. And doing it using zero trust principles, so really moving away from that old VPN model entirely. And the core tools we are focusing on today are Cloudflare Warp, which sits on the user's device, the client, that's our endpoint connection, and Cloudflare D, which is the piece you run inside your private network, connecting your applications, your servers, the daemon side. And the real challenge we are tackling here is bridging these ephemeral private IP spaces, where things change constantly, connecting those back to authenticated remote clients, people working from anywhere without opening up security holes. We look into Cloudflare local domain fallback that allows you to direct DNS queries to a dedicated local resolver, as well as the most recent Cloudflare addition, Hostname Routes. Okay, let's dig into that. Starting with the client, I got Warp installed on my laptop. Let me connect to the network. What happens next? Well, first thing, we can run some diagnostics. If we run a Warp CLI debug network, it provides physical network configuration of our interfaces. We also see there's a local DNS proxy. It's used by the operating system as its resolver. Basically, all DNS queries go to the local DNS proxy and then are forwarded to the Cloudflare via the encrypted tunnel. So we could say the local Warp client intercepts all our DNS queries, and it creates a virtual network tunnel interface. That's our secure on-ramp. Traffic to the Cloudflare network is being routed through this virtual interface. And if we check Warp CLI tunnel stats, we can see the protocol it's using. Usually it's either mask that runs over QUIC or WireGuard. And it shows the peer endpoint it's connecting to. And that peer IP, that's the public Cloudflare Edge server IP. It's an Anycast IP, so it automatically connects us to the nearest Cloudflare data center, the closest POP. That's how they keep the latency down. You want to see ideally under 30 milliseconds for excellent, maybe under 50 milliseconds for good. It makes a huge difference to the user experience. Now, we need to enroll the device into our company Zero Trust setup. To do that, let me go to Preferences, Account, and log into Cloudflare Zero Trust. You can find the organization name, also called the team name, in the Cloudflare Zero Trust console under Settings, Custom Pages. Let me put it here and click Done. Then we need to log in via an identity provider. Think Google, Microsoft Entra ID, Okta, whatever you use. Warp needs to know who you are. That's the identity part. I have my identity provider set to Microsoft Entra ID. Let me log in, and that's it. If we go to Settings, Preferences, Account, we'll see that our device is now part of Cloudflare Zero Trust domain. Once we authenticate, the Warp client gets assigned an IP address. Now, this isn't just any IP. It's an IP from the CGNAT range, like 100.64/10. It's an internal private IP within the Cloudflare ecosystem. It lets enrolled devices talk to each other securely and, crucially, access those private on-prem resources later. Let's confirm that our client is connected. I will head over to the Zero Trust console under My Team and Devices. There's our client machine. If we drill down into the details, we can see it's connected to a Cloudflare POP in Poland. Scrolling further, we get the client IP address details along with the user who enrolled the device. There's also our tunnel IP. Okay, client side sorted. Now the messy part, the private network. Our application runs on Kubernetes. We have two pods running. One hosts a simple Alpine Linux container, and the other runs our WhoAmi application. WhoAmi is a very simple and lightweight web server that we'll use to test our connectivity. These pods are designed to be disposable. They get an IP from the 10.244 network. Let me enter the Alpine shell and call the WhoAmi application running on the other pod. The output shows that the request was sent to the .70 IP and the source IP of the calling pod was .67. Now, the thing is, we cannot rely on the pod IPs. Trying to pin down access based on those pod IPs is asking for trouble. Those IPs are constantly changing. Let me simulate a pod being restarted. I will remove the whoami pod. We see a new one being created with a different IP. So the key takeaway is that modern infrastructure is dynamic. Whether you are using Kubernetes pods, spinning up OpenStack VMs, or just launching any standard cloud instances, their IP addresses are ephemeral. They get assigned dynamically, and if a component dies and restarts, it gets a completely new IP address. So what's the stable thing? How does Kubernetes handle this internally? That's where the Kubernetes services abstraction comes in. It gives you a fixed IP address from a different range and a stable DNS name. And that service IP doesn't change even if the pods behind it do. The service knows which healthy pods exist at any given moment and directs traffic accordingly. Let's go to our Alpine shell and try calling the application, but this time via its service IP. Success! Now, if I remove the whoami pod, it gets recreated with a new IP, but I can still reach it through the same service IP. This concept of using a fixed, stable endpoint to manage traffic to dynamic resources is a common pattern in modern infrastructure. Similar concepts apply to Docker networks, cloud instances, or even bare metal. You usually put a load balancer, reverse proxy, or a service mesh in front of your application to ensure reliable access regardless of changes to the backend components. So, how do we connect the private network containing the service out to Cloudflare Edge? That's Cloudflare's job. It makes an outbound connection to Cloudflare Edge, initiates the tunnel from inside our private network. We don't need to open any inbound firewall ports on our firewall. No port forwarding, no holes poked from the outside. Our private network perimeter remains completely sealed. To connect Kubernetes to the Cloudflare Edge, we'll run Cloudflared as a pod within our Kubernetes cluster. First, let's perform all the setup outside of Kubernetes and then pass all the configuration to our pod. I have Cloudflared already installed. First, we need to authenticate it with our Cloudflare account. To do that, I will issue the Cloudflare tunnel login command. We'll get a URL to log into our Cloudflare account. Let me open it in a browser. Since I already have a web session open with Cloudflare, I am prompted to authorize the Cloudflare daemon to create and manage tunnels for the Linux Cloud Hacks of VH domain. After authorizing, a certificate allows us to create new tunnels. This certificate is saved in the Cloudflare directory. Now we can create a new tunnel, which I will call my tunnel. The tunnel is created and its credentials are saved to a file. If we check the Zero Trust console under Network Tunnels, we'll see a new tunnel listed. But it's currently inactive. As we want to run Cloudflare as a Kubernetes pod, let's prepare its configuration. To keep things secure, I will load the tunnel credentials into a Kubernetes secret. Next, we'll apply a manifest file that deploys a Cloudflare pod. Nothing fancy here. We are just using the official Cloudflare image. This pod brings the tunnel up with a specific configuration. The credentials are pulled from the secret and the configuration is defined in the manifest below. Normally, you would configure a reverse proxy with an ingress resource, but in this case we are simply connecting the pod directly to the Cloudflare network. Let's apply the manifest file. The Cloudflare pod starts up, and if we check the logs, we can see that Cloudflare has established a secure tunnel to the Cloudflare Edge. In the Zero Trust dashboard, the connector shows as healthy. Clicking on the connector reveals more details, such as the tunnel source IP and the data center it's connected to. You can run multiple connectors, and Cloudflare will automatically load balance traffic between them. Okay, both our client and our Kubernetes cluster are connected to Cloudflare under the same Zero Trust domain. Next, we need to tell Cloudflare, hey, if the Warp client wants to reach that Kubernetes service network, send the traffic down my tunnel. In other words, we need to somehow advertise to the rest of the network that our service is available behind this particular tunnel. It's especially important if you have multiple tunnels to different locations. Let's look at our cluster. We won't be accessing pods directly since they don't have a stable IP. Instead, we'll advertise the service subnet. To do this, I will list the tunnels and then use the tunnel route @IP command to advertise a route to the rest of the network. Here we are advertising the /16 range, which covers the entire service network. Next, we specify the tunnel name. Okay, we've just added a route to the 10.96/16, pointing to our Cloudflare D tunnel. Essentially, we've told Cloudflare to forward all traffic for that network range through the tunnel. We can confirm that with the tunnel route IP show command or by checking the Zero Trust console under Networks, Routes, and we'll find that route pointing to the tunnel. Of course, you can also add the route via GUI by clicking Create New Route, entering the network range, selecting the tunnel, and clicking Create. Okay, route added. Moment of truth. Let me note down the service IP. I will go back to our Warp-enabled laptop and I will try calling the service. And it does not work. Connection failed. Okay, wait. Why? This stumps so many people. The tunnel is healthy, the client is enrolled and authenticated, the route is advertised from the private network through the tunnel. Why isn't the traffic getting there? Let's trace the route to that IP. We see the traffic is directed to the default gateway and not to the tunnel. But why? It's because of a default setting in the Warp client profile that catches almost everyone out. It's called split tunneling. That lets you decide which traffic goes through the secure Warp tunnel and which just uses the regular internet connection. And by default, the Warp client is often configured to exclude common private IP ranges from the tunnel. Critically, this usually includes the entire 10/8 range, the whole 10.network. So, if my destination is 10.96.190.109 and the split tunnel rule says exclude 10/8, the Warp client doesn't even try to send it down the tunnel. It just hands it off to the local operating system's routing table. And the OS sees a private 10.x address, it knows that's not routable on the public internet, so it sends it to the local default gateway, which promptly says, I don't know where this private network is, and just drops the packet. It never even reaches Cloudflare. That's subtle, but makes total sense why it fails. It's the client deciding not to use the tunnel because of that default exclusion. The fix feels a bit weird if you are used to traditional VPN where you define everything server-side. But it's simple. We go into your Cloudflare Zero Trust dashboard, find the device profile settings for Warp, and then find that split tunnel configuration. Here's the list of all ranges excluded from being routed through the tunnel. And now we remove the 10/8 exclusion. You can make it more specific if needed. But for this case, removing the whole 10/8 tells Warp explicitly that traffic for the 10.96 network must go through the tunnel. The Warp client should pick up the change. Now we try connecting to 10.96.190.109 again, and it works instantly. If we look closely, we'll see the request is coming from the 10.244.0.77. That's the IP of our Cloudflare D pod. Let's go over the data flow. The client requests for the 10.96/16 network. As it is no longer excluded, it goes through the secure tunnel to the Cloudflare edge. The Cloudflare gateway applies any relevant network policies based on identity. It sees the destination IP matches the route advertised by my tunnel, sends it down the tunnel to Cloudflare pod running in Kubernetes, which forwards it to the actual WhoAmi service IP. Importantly, when the traffic arrives at the service, the source IP address it sees is the internal IP of the Cloudflare D pod. So the service knows how to send a reply back to Cloudflare pod, which then sends it back through the tunnel to the client. The return path works. We have secure IP level access, but nobody wants to remember 10.96 whatever address. We need DNS. We want to type a domain name. Let me go to my test Alpine pod and try calling the service by its name. Works. But how is that possible? If we look at our pod DNS resolver configuration, we'll notice a few things. First is the DNS resolver. Inside Kubernetes, we've got core DNS, which handles resolving those internal names to the stable service IP. The second thing is the search directive. It defines domains that will be appended to hostnames when you try to resolve them. If I ask for WhoAmi hostname, it automatically appends the default SVC cluster local domain. Now the n-dots parameter tells the resolver how many dots a domain needs to have to be considered absolute. If a domain has 5 dots, it will try to resolve it. If it has less than 5, it will try appending the domains from the search list. Lastly, in Kubernetes, the domain name is built like this: service name, namespace, and then SVC that indicates a service, then the default cluster domain suffix configured during cluster setup. That's great, but the Warp client, where does it send its DNS queries? By default, Warp sends all DNS queries up to the Cloudflare Gateway resolver, which is great for security filtering of public sites, but it doesn't know about our private SVC cluster local names. So, how to solve that? One option is to have the client query the Kubernetes core DNS server directly, but that's not ideal. A better approach is to use a feature called Local Domain Fallback, or LDF. It's pretty convenient. You configure Warp and say, hey, if you see a DNS query ending in SVC cluster local, don't send it to the gateway. Instead, send it directly to my internal DNS server. Let me go to Zero Trust console, then Settings, the default profile, and then Local Domain Fallback. This list here is the list of domains that should be resolved by an internal DNS resolver rather than Cloudflare Gateway DNS resolver. I will remove the local domain from the list and configure Kubernetes core DNS to resolve any domain that ends with SVC cluster local. So we've told Warp, for this specific domain, bypass the Cloudflare resolver and ask the On-Prem resolver directly. Let's test it out. On our client device, I will first check the DNS fallback domains. The SVC cluster local domain is on the list, which means it will be resolved locally and not by the Cloudflare gateway. Now, let's try resolving the WhoAmI service by its domain name. Success! The DNS query was forwarded to the core DNS server. Next, let's confirm we can access the service using that domain name. That also works. Client can now resolve domains under SVC cluster local and securely connect to services running inside our Kubernetes cluster. This approach, combining routes with local domain fallback, isn't limited to Kubernetes. It also works with Docker environments, cloud instances, or even on-prem setups that use a private DNS server. Let's take it a step further. Suppose we want to selectively allow access to our service for specific users only. Cloudflare is identity aware, meaning it can enforce policies based on who the user is, not just their IP or network. Since all traffic between the client and the service flows through Cloudflare Gateway, the simplest way to restrict access is by applying firewall policies at the gateway. First, I will copy the target IP of our WhoAmI service. To create a firewall policy, we'll go to Gateway, Firewall Policies, Network, Add Network Policy. Let's give the policy a name and identify the traffic by setting the destination IP to match our service IP. Next, we'll apply the rule based on the user's email identity. Here's how that works. Cloudflare Gateway integrates with the Cloudflare Warp client, which runs on users' devices. When a user logs into Warp, they authenticate with our chosen identity provider, in this case Azure. This authentication gives Cloudflare the user's identity in the form of their email address, which we can use as a condition in firewall policies. Now, let's set the action to block and click Create Policy. Time to test. I will open a browser on the client and try to access our service URL. As expected, access is restricted. IP-based policies tied to identity work well, but here's the catch. We often need more granular control. Instead of relying only on IPs, which can change, we want policy based on host names. For example, we might allow access to app1 default SVC cluster local, but block admin panel default SVC cluster local. That's the essence of modern zero trust approach. So let's go to the gateway, then disable the IP-based firewall rule. Next, let's try the connection. All good. Now we create a DNS policy instead. We'll say block DNS queries for WhoAmI default SVC cluster local if the user is user1 at our Entra ID domain. Let's set the action to block. Seems straightforward. Let's put it to the test. I will go back to our client browser and refresh the page few times. We connect without any issue. Let's try to resolve the domain. Also works. How about calling the service from the command line? Also works. Wait, why did the DNS policy fail? The policy isn't a gateway. But remember local domain fallback? We told Warp if the query is for SVC cluster local, bypass the gateway resolver. So the DNS query never actually reached the Cloudflare gateway where the policy lives. Local domain fallback sends the query directly from the Warp client over the tunnel straight to the internal Kubernetes core DNS server. The gateway is completely bypassed for the DNS lookup. No query seen, no policy applied. That's a massive gap. We've created a policy bypass just by trying to make internal DNS resolution work conveniently. It's a trade-off that many people don't realize they're making. You get easy resolution, but you lose hostname-based policy enforcement for those internal names. Okay, this is clearly not ideal. We need both usability, access by name, security, and gateway policy enforcement. How to fix this loophole? This leads us to the really quite elegant solution using what Cloudflare calls Hostname Routes, which relies on synthetic IPs. The core principle is, if you want the gateway to apply a policy based on a hostname, the DNS query must go through the gateway. No bypassing. The first step is disabling local domain fallback for SVC cluster local. I will disable our DNS block policy, then let me go to settings, Warp client, edit the default profile and select local domain fallback. Now let me remove our domain from the list. Now, DNS queries for that domain will go to the Cloudflare gateway, but the gateway still doesn't know the internal IP address for our service. Next, let's go to split tunnel configuration and remove the CGNAT range so that all traffic falling under 100.64/10 will go via the tunnel. We also need to make another change. Remember that IP row we added earlier? 10.96/16 pointing to the tunnel? Let's delete it. Okay, we've removed local domain fallback, removed the IP route. What replaces them? We add a different kind of route, a hostname route. Let's go to Hostname Routes and click Add a hostname route. Here we tell the gateway that whoami default SVC cluster local domain is behind my tunnel. Okay, so a route based on the domain name is pointing to the tunnel. How does it help? Watch the flow. It's pretty neat. Our Warp client sends a DNS query for whoami default SVC cluster local to the Cloudflare gateway, because local domain fallback is off. The gateway sees the query, it checks its DNS policies first. That's because the query reached the gateway this time. Let's say the policy allows it. The gateway sees the query, matches the hostname route configured for my tunnel, so the gateway itself forwards the DNS query through the tunnel to Cloudflare D pod running inside our network. Cloudflare D receives the query, asks our internal core DNS server, which replies with the real internal IP like 10.96.190.109. Cloudflare D sends that real IP back through the tunnel to the gateway. Here's the magic. The gateway does not send the real 10.96 IP back to the client. Why not? We remove the IP route. The client wouldn't know what to do with it anyway, right? Instead, the gateway generates a synthetic IP address from the same CGNAT range, like 100.80/16, and sends that synthetic IP back to the Warp client as the answer to the DNS query. Okay, so the client thinks whoami default SVC cluster local resolves to some 100.80 address. And the client then tries to establish a TCP connection to that synthetic IP address, which goes where? Back to the Cloudflare gateway, because all traffic is going through Warp. The gateway intercepts this incoming connection destined for the synthetic IP because the gateway issued that synthetic IP in response to the original DNS query for whoami default SVC cluster local. It remembers the mapping. It knows the connection to the synthetic IP is really meant for the private hostname. So now, the gateway can apply any relevant network policies like session duration, posture checkouts, and so on. Then it performs destination NAT. It rewrites the destination IP from the synthetic IP back to the real internal IP, 10.96.190.109, and sends that rewritten packet down the tunnel to Cloudflare D, which forwards it to the actual Kubernetes service the connection establishes. That is remarkably clever. We forced both the DNS query and the subsequent data connection through the gateway policy engine, using the hostname as the identifier, even though the client only ever sees a synthetic IP. We get hostname-based policy enforcement without the client needing direct IP routing to the private network. And if someone did somehow know the real internal IP, 10.96.190.109, and try to connect directly, it fails, because we removed the IP route for 10.96/16. The gateway has no instructions to send that direct IP traffic down the tunnel anymore. Access is only possible via the approved hostname route. That completely closes the loop. Access is by name, policies are enforced by name, and direct IP access is blocked. It's a really powerful model. Since all the traffic passes through Cloudflare Gateway, we can also apply DNS policies. I will head back to the Firewall section and enable a DNS policy that blocks access to our application from the client. Let's test it. From the client console, I will try resolving our application's hostname, and we get a refused reply. That indicates the resolver is denying the request for policy reasons. Can we work around it? Let's try connecting via the synthetic IP. No luck. How about the original IP? That fails too. The policy is working as intended. So let's recap. The key takeaways are: first, the Kubernetes service abstraction is vital. It gives you the stable IP target. Second, be very aware of the default split tunnel settings in Warp. 10/8 network exclusion is often the culprit when private network access fails unexpectedly. You need to make sure Warp knows to send the traffic through the tunnel. You have to explicitly include your private ranges. And third, if you need granular hostname-based policy enforcement on private resources, local domain fallback is a trap. The synthetic IP mechanism enabled by hostname routes is the way to go. It forces everything through the gateway. It ensures zero trust principles are applied consistently, even for your internal domains. We replace the network boundary with an identity boundary effectively. Okay, so here's a final thought to leave you with. We focus heavily on Kubernetes here because it exemplifies that dynamic, ephemeral environment. But the pattern itself is much broader. Think about this model. Routing internal resources via a secure edge like Cloudflare using identity-aware hostname routes and enforcing policy at the edge. Could you apply the same template to grant selective, secure, audited access to, say, VMs or internal Docker applications, or even traditional on-premise systems that were previously only reachable via VPNs? It offers a way to bring modern zero-trust governance and fine-grained access control to parts of your infrastructure that maybe haven't seen it before, all based on who the user is and a specific name of the resource they need, not just the network segment they are coming from. Something to think about. Thank you for watching and see you in the next video.